Cool. So what exactly I mean by this, I'll say in a second. But for now, let's just assume that we could build such a thing, and let me call it bar of X. So there's a couple of sort of desirable properties we'd want for such a construction. So first off, we'd want it to not be able to distinguish between spaces that have isomorphic homology groups. So if I have a map of spaces, X to Y, that induces an isomorphism on homology, then if these constructions are capturing just the homological information about X and Y, then I would want to have a weak equivalence here. And from now on, every time you see like an H star, this really means like reduced homology, integer coefficients, but just trying to declutter notation. So that's one thing you'd want. And then you'd also want some sort of relationship between X and this completion, or and this construction rather. So you'd want a comparison map, and you'd at the very least want that to be like a homology isomorphism if this bar of X is supposed to be capturing the homology information of X. So that's sort of the starting point. That's our goal. And so now I'm going to talk about, well, how you might build such a thing. So a place to start, and just remind us, this is what we're aiming for. That's what we want. So one place to start would be essentially with a Hurewicz map, right, which relates homotopy groups to homology groups. And one way to build that map, one way to construct it is as follows. So first, you realize, or rather, when I say spaces, I really mean like a pointed simplicial set. If you're not familiar with that language, a simplicial set is just a delta op shaped diagram in sets, and it's a model for spaces. There's equivalence between simplicial sets and regular topological spaces. So pretty much whenever I say space, I really mean simplicial set. And there's an adjunction between simplicial sets and simplicial abelian groups. So how does this thing work? Well, if you give me a diagram of sets, so a simplicial set, then on each of those sets, I can form the free abelian group. And that would then give me a delta op shaped diagram in simplicial, or rather in abelian groups, i.e. I'd have a simplicial abelian group. And that's what this functor z tilde does. So that's my left adjoint. And then, of course, I can forget the extra structure of being an abelian group. And so I would have this forgetful functor u going back to simplicial sets. So I got left adjoint on top, right adjoint on bottom. And with any adjunction comes a unit map, right? So I have a natural transformation from the identity functor to this uz tilde guy. Now I started talking about all this by mentioning the Hurewicz map, and the neat thing is that this is a spaces level Hurewicz map in the following sense. So this isomorphism here tells me, well, okay, so the homotopy of this uz tilde guy is exactly the homology of y. And if I apply homotopy groups to this map here, so that's all I've done here, composed with this iso, I get exactly the Hurewicz map from homotopy to homology. So it's a good way to think about this is as a spaces level Hurewicz map. What this tells us is that this uz tilde construction satisfies this first property we want. So just to be clear, right, having this homology isomorphism means that for each star, I have an iso between homology of X and homology of Y, but that's exactly the homotopy groups of uz tilde. And that's exactly the homotopy groups of uz tilde Y. So I get an iso here, and so I get my weak equivalence between uz tilde X and uz tilde Y. So it's a good place to start, but it's also not tremendously difficult to check that you usually don't get the second property. You usually don't have a nice relationship between x and uz tilde of x. A good example would be to look at what happens with like the two-sphere. So, okay, so it's not exactly what we want, but it's a good place to start. And to improve this construction, I'm just going to fatten it up. I'm going to iterate what I just did. So what I mean is the following. We have this adjunction, comes with this unit map. What we did in the last slide was just look at x going to uz tilde of x. And I said, okay, that's a good place to start, but it's not exactly what we want. So how do I expand? How do I fatten up this construction? So one way to do this is to realize, well, this uz tilde is really like the identity functor applied to uz tilde. So nothing crazy happening here. But once you write it like this, you see, oh, hey, I could apply the unit map to this entire uz